Welcome to Things I Wish Someone Had Told Me When I Was a Sophomore. My name is Keith Hollingsworth. I'm the chair of the Mechanical and Aerospace Engineering Department. And this is a lecture covering various topics about the curriculum and why we teach you the things we teach you. I call this Things I Wish Someone Had Told Me When I Was a Sophomore because I believe that you'll benefit from understanding what you are in the middle of going through and why you're going through it, and I wish someone had told me that too. The first thing we're going to talk about is we're going to try to find some motivation for your studies that will perhaps help you study a little longer and a little more thoroughly. And to do this, we're going to talk about engineers, scientists, and inventors. Then we're going to talk about the MAE curricula, why they are structured the way they are, so that you'll understand why we've made the choices we made. And then I'm going to talk about some advice for your coming years in our program. So let's start by talking about engineers, scientists, and inventors. I've been giving mentoring talks in various classes at two different universities for almost 20 years now. And back around the year 2000, I devised this little quiz that I would give at the beginning of my talks back when they were held in classrooms. So imagine, we're not going to do the quiz today given the format, but let's imagine doing it. So take your imaginary piece of paper and draw these lines on it so that you have 3 columns. And label the columns scientists, inventors, and engineers. And what we're going to do is imagine listing some names of famous scientists, inventors, and engineers. But before we do that, I want to have a discussion about what these people do and what makes the difference between them. A scientist is a person who adds to the knowledge base. He or she is done when a new piece of science has been verified and added to the knowledge base of humanity. Along the way, the scientist may invent, but that isn't necessary. Inventors are people who create new technology. And in general, they are not required to use science or engineering in the production of this new technology. They can, in principle, invent in their garages without doing any calculations or without knowing anything about the science that makes their invention go. Engineers, on the other hand, use science to create and to control technology. This is what separates us from standard, the general inventor, because when we invent, we make the calculations, we have the ideas, we refer to concepts that allow us to create new technology based on a strong foundation in the sciences. And this second part about controlling technology is extremely important. I would guess that for every engineer who gets to invent over the course of their career, there may be 100 engineers who do not invent but spend their careers controlling existing technology. This is very common and it's very important. So, before we start writing down names, there are a few rules. The most important rule is that these people have to be famous in the general population. And so I'm going to qualify that by saying that the name has to be sort of a Wikipedia level known name. And this keeps us from short-circuiting this little quiz by naming our parents, if they happen to be engineers, or our aunts or uncles, or just writing down names of UAH faculty members. So these would be people who would be recognized by a student, on the other side of the country, for example. All right, some more rules. I found over the years when I do this that mostly students don't know who is an engineer and who isn't. So let me take some of the names off the table. Howard Wolowitz, the famous engineer character in The Big Bang Theory, is not eligible because he's not real. Steve Jobs was a marketing and business person, did not have a degree in engineering. Bill Gates is a programmer and famous CEO, also not an engineer. Elon Musk is a little closer. He has BS degrees in physics and economics, but he too is not an engineer, but he certainly has a tremendous talent in hiring good engineers to do the things that his companies are involved in. And then finally, Thomas Edison and Henry Ford, as famous as they are not degreed engineers. We'll see them in a different context in a moment. So, with those rules in place, imagine taking a few minutes, 5 minutes, let's say, and writing down 3 names for scientists, 3 for inventors, 3 for engineers. Scientists, that's easy. Our K through 12 educational system is really good at celebrating famous scientists, and so most people write down Newton, Einstein, and Galileo more or less in that order. There's also Madame Curie and Werner Heisenberg and James Clerk Maxwell and a number of other people. Inventors, also easy. Here we find Edison and Ford, and usually people will put Alexander Graham Bell or maybe Marconi, and there are a wealth of others that are celebrated in our culture because inventions have a way of directly affecting the population, and so those names get known, particularly after about 75 or 100 years. But what about engineers? Most students that have taken this quiz over the years can't write down a single name, not one. And this was so interesting to a friend of mine, John Leonhardt, who back 20 years ago was writing and performing a daily radio show on creativity for the National Public Radio Network. He actually did an episode about this quiz. And so it's interesting because here you are as an engineering student, and maybe you find filling this column difficult. If you do, you're in the great majority. But I find this unusual. It's interesting that a young person would choose a college major with no reference frame to the famous people who are graduates and from that major who got famous. For example, if you were in film school at UCLA, I'm sure you could name your 3 favorite directors. If you were in acting school in New York, I'm sure you could name your 3 favorite actors. If you were a cello student at Juilliard, I'm sure you can name the 3 cellists who you most admire and who most inform your playing style. So, if you're a creative writing major, I'm sure you could name your three favorite novelists, for example. But engineering students have a tough time with this. And I think the reason is that in the corporate world, a lot of engineering is done behind the screen. The names of the people who give us the great products of today are not known. We know Steve Jobs for his skill as a CEO and as an industrial designer, but it's hard to identify the names of the actual engineers behind the iPhone. And this is an issue which I hope we can improve upon today, because I think if you knew names of great engineers, particularly in mechanical and aerospace engineering, then and learned about them, then you would have somebody to think about while you fashion your career. So let's do that. Here's some engineers to get to know. And this is a dense slide. I did it on purpose because I want to leave you with the impression that there are a lot of folks out there. And indeed, I could have made a number of pages like this, but I have time for one. And these are some of my personal favorites. And a lot of them were in the thermal fluids area because that's my area. And these are people who have impressed me in going through learning at the various degree levels that I went through. So let's very briefly introduce you to each one of them. The first one is Isambard Kingdom Brunel. He makes the list because of two reasons. One is it's generally acknowledged that he was the greatest engineer in the world around about the early 1800s. The second reason is he has the coolest name of the list, Isambard Kingdom Brunel. This is the man that gave us the large steam-powered railway systems that mark the early 1800s. Okay? He was a British engineer, but he was educated in France and Paris, and he gave us steam power on a large scale, and that includes steamships. He had some very large, for his day, steam-powered ships. He also now has a university named after him, Brunel University. The next person is Josiah Willard Gibbs. Albert Einstein said that Josiah Gibbs was the greatest scientific mind that the United States has ever produced, and I think he was certainly right at the time that he said it. Except Gibbs is an engineer. His degrees were in engineering. In fact, he got the first PhD granted in engineering in the United States, and that was a degree in mechanical engineering. It had to do with gear teeth. And that PhD was, I believe, the sixth PhD of any kind in any field given in the United States, and that was in the neighborhood of 1865. Gibbs made fundamental contribution to the theory of thermodynamics. He invented, separately from Ludwig Boltzmann, the entire field of statistical thermodynamics. He wrote the most complete definition of entropy from statistical thermodynamics. He also made tremendous advancements in thermodynamics applied to chemistry. This was just an absolutely towering person to get to know, and was one of the greatest mechanical engineers. Nikola Tesla, everybody sort of knows Tesla as a great inventor. He was a degreed mechanical engineer from Croatia. He invented AC current, the Tesla coil, radar, a bunch of other things. Bertha Lamy was the first female degreed mechanical engineer. She got a degree in mechanical engineering, BS level from Ohio State in 1893, and had a degree. Had a career, I believe, with Westinghouse as a mechanical engineer. Frederick Lanchester was one of the fundamental. Let me get down here with my pointer here. Was one of the persons who did fundamental advancements very, very early in the history of the invention of the automobile and the airplane. He has a tremendous number of patents in both areas. He was a British engineer, so this was an engineer who did a lot of inventing. He also makes the list because he came up with something called boundary layer theory, which is the foundational theory for modern viscous fluid mechanics, and he's the one who proposed it the first time. Theodore von Karman is the king of early 20th century fluid mechanics. He was Hungarian by birth. He was educated in Germany. He got his PhD with Ludwig Prandtl at Göttingen. He was a professor at Aachen, and then when World War II came along, he immigrated to the United States, where he became a professor at Caltech and the founding director of the Guggenheim Aeronautical Laboratory at Caltech, which is Gauset. He and one of his PhD students founded the Jet Propulsion Laboratory, now known as NASA JPL. He and another of his graduate students founded the Aerojet General Corporation, which exists to this day as Aerojet Rocketdyne. And he founded, I think, a couple more companies. He made fundamental advancements in turbulent fluid mechanics, just a towering figure. Donald Wills Douglas was the first aerospace engineering graduate of MIT, and he then founded the famous Douglas Aircraft Corporation, which was a pivotal and highly inventive aeronautical corporation in the mid-20th century. Douglas and his fellow engineers there created some of the most famous designs for aircraft of that time. Everybody here in Huntsville knows about Werner von Braun. He was a German aerospace engineer who invented and directed the production of the V-2 missile, and then later the entire Saturn V system that took men to the moon. John Kiker was an incredibly talented NASA engineer, aerospace engineer. He did a lot of things for NASA, the most famous being he's the person who came up with the crazy idea of transporting the space shuttle by placing it on the back of a Boeing 747. This was such a crazy idea that NASA literally wouldn't let him work on it, wouldn't give him the wind tunnel time. So he rented a pickup truck, installed his own force balance system into the bed of the pickup truck, put models of the shuttle and the 747 on the force balance, and then drove the pickup truck up and down the runway at Ellington Air Force Base in Houston, Texas, acquiring the wind tunnel data that he should have been able to acquire in a wind tunnel. With that data, he came up with a way to fasten the two planes together and the necessary flight attitudes to get them to fly together, to get them to disconnect safely in midair, all of that. He demonstrated that with models that he built, and his model flying club flew for the NASA brass. And at that point, they gave him the the resources to go forward. He also designed all the parachutes for the NASA missions of the 1960s, the parachutes that allowed the capsules to land, and he also designed and built the flag that was used on the moon. Geneviève Comte de Belleau is a famous French fluid mechanician. She came to America and worked with a man named Stanley Corson at Johns Hopkins and made fundamental advances in turbulence and aeroacoustics. She went back to France and was the director of one of their major fluid mechanic institutes there. And she has won numerous awards both in France and in America. Boris Rubinsky is a professor at Berkeley, and he's a thermal scientist who invents cryosurgery tools. In fact, he pretty much founded the field of ultrasound cryosurgery, and he has been president of the College of Cryosurgeons, even though he is a mechanical engineer and not a physician. That's how well thought of he is, and it's an example of what somebody can do moving into the world of biomedical engineering. He's also founded, I believe, more than 5 companies. So this is just a brief list. There could be many more here. I suggest that you get to know some of these people and you find people in your own particular area. If you're interested in controls, if you're interested in mechanics, if you're interested in material science, there are people there waiting for you to learn about. And it's not hard to do it given the internet these days. Okay, so let's move on to the next topic in our discussion, and that is, why is the ME or AE curriculum what it is? Okay, so let's talk about that for a while, and then we'll talk about how it's structured. First thing I want to say is that the curriculum was not invented to torture you. The content, the text selection here at UAH is very similar to most accredited engineering schools. The National Accreditation Society, which is called ABET, helps make this so. So if you're wondering if the experience that you're undergoing is in some way additionally complicated or would have been different if you'd been somewhere else, the answer is that the content and even the textbook selection is pretty much uniform across the country. So now let's deal with the next question: education versus training. Specifically, should we spend most of our time with you, training you in the engineering codes and practices of the day, or educating you so that you can apply the foundational sciences to new technical problems? Okay. You can train a person without having them understand why what you're telling them is so. If you educate a person, the education should make it clear to them why the facts and the techniques, problem solving that you're teaching them works the way it does. There is a big difference. And this is an interesting question. The answer to this question has actually changed over the course of time. You would have gotten one answer in, say, 1900 and another answer today. So let's see where we are today by looking at an example. And that example is going to come from the past. I take you to now a general store in a little town in eastern North Carolina. The town's called Mount Olive. That's where the pickles come from, in case you're wondering. And this is a picture of that general store in 1914, okay? A little over 100 years ago. So you're basically looking at a kind of mini Walmart of the day. And let me get the pointer going here. And let's take a look because you can tell a lot about the technology of the day by looking at the consumer products of the day. And that's what I'm suggesting that we do. Well, right away down front, you see we've got some feed sacks. Up on the top shelf, we have some wind-up clocks. The shiny things here are globes for oil lights, because even though electricity had been invented by 1914, it really hadn't gotten to the South yet. Okay. If we look over here, we see bolts of cloth so that people could come in and buy cloth and go home and make clothes. We do see a few ready-made clothes here. These are probably overalls, not unlike the pair this gentleman has on. Unfortunately, we can't see his face. We can't see the little kid standing behind him there. And when I looked at this, my eye was drawn to these vertical things hanging from the ceiling. And my first thought is that they were fishing poles. But I talked to somebody who knew a little more about this picture, and he said, no, these are buggy whips. So the proprietor of this store decided that, the product of the day, the thing he wanted somebody to see when they came in the store, and this picture is being taken from essentially just inside the front door. The thing that people would come in and see were buggy whips, because again, even though the automobile had been invented, and in fact inexpensive automobiles had been invented, they really hadn't gotten to the South in large numbers yet. So people were still needing to go around in horse and buggies. So this would be the state of affairs technology-wise in 1914. Now let's focus in on the two gentlemen standing on the right. This is the proprietor of the store, and this is his 17-year-old son. Okay, and it's got this cool hat here. So 17 years old, in today's world, he would be perhaps a senior in high school, and would be, if this were September when this picture was made, I don't know when it was, he would be applying to colleges in today's world. So the question is, if he were to apply to an engineering college in 1914 and be accepted, what would happen over the course of his career, and would that college give him the best preparation for that career by training him in the technology of the day, or by educating him in the math and science fundamentals? The nice thing about looking backwards is that we can know the answer. So let's play that little game. Should this potential engineering student be trained to do the engineering of the day in 1914, or educated in the fundamentals? Okay. Well, we know that 12 years before this picture was taken, George Carrier invented modern air conditioning. Hadn't gotten to the South yet, but when it did, it would revolutionize living conditions in the South, indeed anywhere in the world where it touched, and would provide an enormous source of income for mechanical engineers, because air conditioning is a big thing. 11 years before the picture was taken, the Wright brothers had their first flight at Kitty Hawk. So the airplane had been invented, but it certainly had not penetrated into normal use yet. 6 years prior to the picture, Ford had invented his Model T production line. The Model Ts were rolling off, but you can see from buggy whips, they hadn't gotten very far yet. 3 years after that picture was taken, our friend Nikola Tesla would propose an early radar system. That's amazing. That would be 1917. Only 11 years after that picture was taken, the first patent would be filed on the transistor. We normally think of the transistor as a very modern invention, but it goes back to, what would that be, 1925. and that patent was filed in Canada. 16 years after the picture was taken, Frank Whittle patents the jet airplane engine in England. So we would get jet airplane engines to go on the Wright brothers' notion of an airplane pretty soon. 22 years later, after the picture was taken, the first operational helicopter flew in Nazi Germany, and in England, a man named Leo Szilard patented the atomic bomb. So if you've ever wondered if the atomic bomb has a patent, it does, and it was filed through the English Admiralty during the time of rolling up to World War II, and it was filed secretively, but it was filed there. 25 years after that picture, we now have regular weekly transatlantic flights on Pan Am. So let's do the math here. 25 plus 11, 36 years. 36 years from that short hop the Wright brothers made at Kitty Hawk to consumers being able to buy a ticket and fly across the Atlantic in comfort. That's amazing. That is one of the most rapid technological developments I can think of. I mean, most of the stuff in my house is older than that. Also, 25 years later, we have the first electronic digital computer, which was built and operated at Iowa State University. And so, we had the transistor 11 years after the picture and the computer 25. And then 28 years later, we have the first ballistic missile test. And of course, this is von Braun's V2 in Nazi Germany. This list of new engineering innovations would get our young person in the picture through about half of his career as an engineer. Just about half. And look how entirely alien these things are from the picture in that general store. How in the world could you train somebody for this when in actual fact, if you're a working engineer, this is what's coming? It's hard to see. And in fact, we're not done yet. If you go just 55 years later to 1969, you have this picture. And this is what I'm going to let you in on a little secret. This young man here is my grandfather, and that's my great-grandfather. My grandfather is the person who introduced me to science and engineering by reading to me when I was a little boy. And he died 6 months before this picture was taken, and he would have loved to have seen it. He was not an engineer. I don't know if the date 1914 rings a bell for you, but it was when America got involved in World War I, and he went into the Navy and for World War I, and obviously he came out, but he did not go to college. All right, so the answer is we're going to educate you in the fundamentals of science, math, computing, design, and we're going to leave training in the codes and practices of engineering to on-the-job experience and to corporate training courses. The resulting model is a 4-year academic degree. Roughly 2 years of that are spent in general college with a math science focus, and about 2 years are spent in the fundamentals of the major. So from our perspective in the Mechanical and Aerospace Engineering Department, we get you for about 2 years. Okay, what do we do with that time? Let's take a look at the structure of your curriculum. And let's start by looking at the mechanical engineering curriculum, okay? And when people who devise college curricula talk and plan, they often use the model of a Grecian temple to represent the mechanics of the curriculum. And so we're going to do that here because that really does work well. All right, the temple will have a foundation, it will have pillars, and those pillars will hold up a capstone. All right, so the foundation is your college education foundation. 18 hours of math, 15 hours of science, 24 hours of liberal arts, and an hour of first year experience. Okay, this is pretty much what everybody in engineering gets. What differentiates you from other majors is what you get in the pillars. The first pillar here is the mechanics and materials pillar. It's 19 hours long. It has in it statics, dynamics, our kinematics of dynamics and machines. That's a lab course. Mechanics and materials, that's another lab course. We have a course in material properties and how they're created by manufacturing, and a course in how to take all that and design machine elements so that they do the job intended and they don't break. The next thing is the thermal fluids pillar. It's really big too. It's 16 hours. It has in it fluid mechanics, Thermo 1, Thermo 2, a course in heat transfer that has a lab, and then a course that sort of pulls it all together and allows you to design thermal systems. That's a senior level course. Then we have a pillar that's in computer-aided engineering. This is where computers really formally enter the curriculum. We start with an introduction to computing engineering 100. Then we go to an introduction to computer-aided design. This is our CAD class, sophomore year. You may be taking that now. Then we go to a course where we use MATLAB to solve engineering problems and teach you the algorithms that are useful in doing that. That's 284. And then at the senior year, we have a course in computer-aided engineering where we teach you how to use the Nastran, Patran package to do sort of real engineering problems at a sort of real level of complexity. And then finally, here's something I call the engineering systems pillar. It's a little smaller. This allows us to knit all this stuff together into workable systems. For that, you need electric circuitry, so we have a course in circuits. You need to be able to take that circuits course and turn that into instrumentation and then measure things with an instrumentation. That's a lab course called 311. Then we bring all this together into a senior course on analysis of engineering systems. And of course, you're going to have to pay for those systems, so you need to understand engineering economics. And then those pillars hold up our engineering capstone, which for us is a 6-hour, 2-semester course where we look at one particular design issue. For us, we have now 6 different design paths through the engineering capstone that include rocketry, aircraft, general mechanical engineering problems, moon buggy. This year we've added electric cars under SAE Electric. There are all kinds of options there. So this is the mechanical engineering curriculum structure. We could go a little more quickly through the aerospace curriculum because there are a lot of similarities. The foundation is the same. There's also a mechanics and materials pillar, but I call this mechanics and aerospace structures because we now include 2 special courses in aerospace structures. They're there because aircraft and rockets have to be very light, and they still have to be strong, and how to design those very special light, strong structures requires its own course coverage. There's also a fluids and thermo pillar. I call it fluids and propulsion. Aerospace engineers take an aerodynamics class instead of fluid mechanics. It's essentially the same course. They take thermo 1, but they don't take thermo 2. They take compressible aerodynamics instead, and they don't take heat transfer or thermal systems. They take a course in propulsion, and here you can choose rocket propulsion or air breathing propulsion, your choice. There's also a computer-aided engineering pillar, but it's one course shy of what the mechanical engineers take. It's identical, except there's no senior level National and Patran course. And on the other hand, the aerospace systems and control pillar is much larger than what we have in mechanical engineering. And this is because aerospace engineering these days is so much about systems level thinking and control thinking. And to do that, we need extra courses. And this is particularly true here in Huntsville, where the military engineering problems that people are employed in solving really do require a systems approach. So there's an introduction to aerospace engineering. There's the circuits and measurements courses. There's the analysis course, same as for mechanical engineering, those three. Then after that, aerospace engineers take a special course in aircraft control. They take another special course in spacecraft design, and everybody does engineering economics. And then they feed into the same engineering capstone. Once you get to the capstone senior design, mechanical engineers and aerospace engineers are intermixed, no difference. Okay, so those are the two engineering degrees, BS degrees, displayed in terms of the structure, so that when we think about making changes, and we do make changes fairly frequently in the curriculum, we think about how those changes affect what we're trying to do in each of those pillars. All right, let me move on to the last element of the talk, and this will be the briefest, some advice. I'd like to start with some do's and don'ts. First one, do your homework, even if it's not graded. Study is a separate activity from doing your homework. Most engineering students think that they're studying when they're doing their homework. That's not really true. Homework should be a check on whether or not your studying has been effective. Studying is when you take the lecture notes, the book, whatever other elements the instructor has provided, and you learn the material. And then you do your homework to see if you learned it. If you didn't learn it, you need to go back and study some more. By the way, doing your homework is different from checking your homework, and let's be clear about that. Second issue, people often ask me, what's the best study technique? And I can tell you from personal experience, the very best study technique is to recopy your notes after every lecture. So, if you're taking notes in a lecture in a classroom, or you're taking notes while you watch an online lecture, even if PowerPoints have been provided to you in some form, you should take notes in those lectures, and that's the second bullet here. And then when you go home, recopy those notes. Sit down every night, relive that lecture by making another copy of the notes. And let, if it's a classroom type lecture, let the memory of that lecture move through you. If it's an online lecture, you can obviously watch it as many times as you want. But there's something about taking the information in through your eyes and ears, processing in your brain, pushing it out your arm to your hand, and writing it down again. There's something about that loop that is the most effective way to learn that I know of. Don't spend your time figuring out how to subvert the system. We often are a little amused when we catch students who spent 6 or 8 hours cheating to avoid 2 or 3 hours of studying. It usually doesn't work, and it's usually a poor use of your time. Practice good manners when you deal with the faculty. Believe me, we can tell the difference. And the best way to do that is to be cognizant of proper titles. All of our tenure track professors can be addressed as doctor or professor. We have currently 6 faculty who are either full-time lecturers or clinical faculty, and they can all be addressed either as Dr. or Mr. depending on the degrees that they have. And I invite you to visit our website, spend a little time figuring out which is which and what to call them. And once you have the right way of addressing people, use it. We appreciate it. Don't email or call the dean or the provost if you want to initiate a complaint. If something's not going right and you need someone to intervene to take a look at the situation, instead follow the following procedure. Your first point of contact is the instructor in the class, because if it's a complaint that he or she can handle, it will be handled most quickly that way. If it isn't, or if the complaint is about the instructor, contact me as department chair or Dr. Landrum as associate department chair, and we'll deal with it. If you go to the dean or the provost with your complaint, all they're going to do is forward that email to me, and if it's something I think the instructor can handle, I'll forward it to the instructor, and so it will go to the lowest level where it has the best chance of being handled quickly and properly. So let's start there if you have a complaint that you need attended to. All right, I want to end up with 2 slides. First of all, I want to talk a bit about your focus while you're here with us. Now, this is going to sound obvious, but in today's world, it really isn't. I want you to try to make your studies your #1 priority during the brief time you are in college. Now, that makes perfect sense, except we all know that in today's world, most of you are working. You're working off campus. You're working 20, 30, maybe 40 hours a week. And very probably your off-campus work is your #1 priority, and your college studies might not even rise to #2. It might be your #3 or #4 priority, depending on what else is going on in your life. Try to make your studies #1 in this brief time that you're here. Let me show you something. If you live to be 85, this is how your life will divide up. The first 18 years of childhood, you'll have 40-some years in a career. You'll have another 18 years in retirement, more or less, and you'll have this little sliver, golden sliver here, will be your time in college. Okay, 4 or 5 years, I'm assuming. This is the last time, as you clock around in this direction, this will be the last time, very probably, that you get to focus only on yourself and what you want. Now, once you get to the blue here, which is where everybody wants to go, but once you get to the blue, you're going to have family, you're going to have bosses, you're going to have mortgages and other issues, and your life will be more complicated than it is now. So if you're really here with us because you love engineering, then do what you love, focus on those studies as your first priority, and let all these other things, if possible, wait until you get to here. That seems like an obvious piece of advice, but in today's world, it is not. And then finally, a parting comment. Kevin Cameron is a person who writes about technology, and I read a lot of what he writes, and every now and then he writes something pretty insightful, and I'd like to share one of his insights with you. In reference to the way engineering works, he says the show goes on, technology expands, and problems are solved. Every door this process opens reveals wide vistas of imagination stimulating ignorance forever. I just really like this quote because it's exactly right. I suspect as a sophomore engineering student, you are not unfamiliar with the feeling of being ignorant. And most people see that word as a negative word. I do not. Ignorance means that, as Cameron says, there's a wide vista of things you don't know sitting out in front of you. And at every point in my career where I've pivoted in my research field, or I've moved from research to management or whatever, I've encountered some form of wide vista of ignorance, and it is imagination stimulating. It gets your juices flowing, and if it's what you love, suddenly there's something about knowing that you don't know much and there's a ton to learn in a particular area that I find very invigorating. And it's when we get comfortable and we have learned enough that we're satisfied, that's when we're bored and it's time to move on. So this process repeats. Every time engineering solves a branch of problems, those problems inevitably reveal additional problems that nobody ever thought about, and accompanied with that new set of problems is this notion of ignorance about those problems. And then we start solving them, and then we loop back around again. This is the essence of engineering as we practice it. And I think I can certainly say in my career this is absolutely true. So I want you to not fear ignorance. I want you to embrace it and be stimulated by it, and do well. Thank you.